Hi folks, we're going to take a look at number 15 from page 418. So here it tells us that Kayla wishes to swim from one side of a river to a point on the other side directly opposite from her starting point. Okay, and they give us the current speed and the speed at which she can swim. And the first thing I want us to do is to find the angle to the bank. Okay, now very carefully here, read that it says to the bank that Kayla should swim in order to go directly across. Okay, so I think we have enough information to draw a diagram. So we'll draw a river here. So say this is where she's starting, and it says that she wants to swim directly across. So when I draw this vector representing her velocity, okay, this is going to be the resultant velocity, in other words, the ground velocity, because this is where she actually wants to swim toward. Okay, so what they want us to figure out is at what angle should she actually be pointing when she swims. Okay, so what we want to do is we want to add up the two vectors that are going to give us this resultant velocity, and that's going to be the vector representing where she's swimming and the vector representing the current. Okay, so if the current is going in this direction, it means she's going to have to aim somewhere in that direction. Okay, so somewhere in this direction here, and notice how I stop at this point because I know that the current is going straight across. Okay, so her velocity plus the current velocity is giving us the resultant velocity at which she's actually going to move. Okay, so let's put in the information that we have. So it tells us that the current is 2 kilometers per hour. She can swim at 3 kilometers per hour because of the current being perpendicular to where she's actually going to be moving. We have a right angle triangle, so this is actually going to be pretty nice. So what I'm going to do here is I'm going to determine this angle, theta, although this is not the angle that we're actually looking for since we want the angle to the bank. So we're actually looking for this angle that I'll call phi. All right, so let's solve part A. So here I'll just use, looks like this is going to be sine, so sine of theta is equal to 2 over 3. So theta is sine inverse of 2/3, and let's get our calculator here and calculate that. So sine inverse of 2 over 3 is, we'll say 41.8. Okay, so in other words, if we're looking for the angle to the bank, which again, I've defined it here on my diagram, so I don't need to define it in words, is just going to be equal to 90 minus 41.8, and that looks like it's going to be, we need to get to 90, so 48.2 degrees. All right, so we've answered A. So let's take a look here at B. It says if the river has a width of 300 meters, okay, so they're giving us the width of the river. Now, I've got to be careful because they're giving it to us in meters, but our velocities are in kilometers. So I'm going to write this as 0.3 kilometers instead of 300 meters. All right. How long will it take for her to cross the river? Well, if I can determine the magnitude of the velocity vector, which is going to be really easy to do here, then I'll have the distance traveled, the velocity at which she's traveling, and I can calculate the time from that. Okay, so here I'll just actually do it in the diagram. Since I can just use Pythagoras, so this is just going to be 3 squared minus 2 squared. So here's square root of 9 minus 4 is 5. Okay, so in B now, I can use my relationship that velocity is distance over time, do a little rearranging, so time is distance over velocity. Okay, so again, we're talking about the time it takes to actually go across, so that's why I'm going to work with this vector here. Okay, so the distance is 0.3, and the velocity, or the speed at which she's traveling in that direction, is, where did we have it, root 5. All right, so that's approximately equal to, and let's get 0.3 divided by square root of 5, and that gives us 0.134 hours. But let's just multiply it by 60 to get the number of minutes. So that looks like about 8 minutes, approximately 8 minutes to go across. All right. So let's take a look at C here. So for C, it says if Kayla's speed in the river river speed had been reversed, explain why it would not have been possible for her to swim across the river. Okay, so let's redraw the diagram with those reversed. So here, if I draw the same diagram, so I'm still looking to get straight across. Okay, there's the velocity she would have to travel at, plus the velocity of the current. And so if we switched over these numbers and made this 2 and 3, well, we can see that that's just going to be impossible, because this has to form a right angle triangle based on the information given. Yet we've got a non-hypotenuse side, which is longer than the hypotenuse here. So here, I guess we can say impossible. Okay, since hypotenuse, hypotenuse, oops, sorry about that, not the longest side. Okay, and that's it for that. Nice and easy. All right, so let's just do a quick recap. So in a lot of these velocity problems, it honestly, the most important thing is to recognize what the resultant velocity is going to be in your diagram. In this case here, since they tell us that she has to go directly across the river, that vector that's going directly across the river is the resultant velocity. And how do we get the resultant velocity? By adding the other velocities that are involved. In this case here, her velocity at which she's swimming, plus the current velocity. And then from there, you can usually then analyze and figure out what you need to find. Okay, that's it for this one.